We are now in chapter 4. In chapter 4, we start going backwards. I'm going to give you the function, and actually, I'm going to give you the derivative of the function, and you're going to give me back what the function was before the derivative was taken. It's called an antiderivative, but you're going to hear me mostly refer to the integral. The process of taking an integral is going backwards, okay? So we know that y is a function of x, right? We're taking that for granted here. Then the derivative of y with respect to x equals f prime, correct? Now, that dx, the differential of x, can come over to the other side so that we have this equation. The differential of y equals the derivative of f with respect to x times the differential of x, okay? That's what this means here. So when we undo the derivative so that we can find the y, we're going to do what's called an integral. This is the symbol. This is the derivative of the function. And this is an operator called a differential. The operator tells us what variable is independent. It tells us, just like dy dx tells me that I have the derivative of the function y with respect to the variable x, this tells me the variable with which I don't know how to say it, that we're going to be finding the integral with respect to the variable x. There you go. Okay, there was supposed to be the word which in that sentence, and I didn't know where to put it, so we just changed the sentence. That's why I majored in math. Okay, so to find the original function, you're going to undo. This is the integral symbol, and this symbol has no meaning without this differential. Got it? They together they work to undo this derivative and give us back our function. So let's start with some basic antiderivatives or integrals. If the function y is a simple x, then its derivative is 1, right? So if I integrate the 1 with respect to x, I get x back. But you see this plus c here. If I was to take the derivative of x plus some constant, I would get 1 plus 0, correct? So when I take an integral of anything, as long as it's just finding the antiderivative, I don't get just one answer. I get an infinite number of answers. It's a family of functions because we don't know, looking at this, if maybe there might have been a constant. We will, at the end of this video, do something called an initial condition or a boundary condition problem that tells me that the function f of x right here, evaluated at a certain value of x, equals an answer, and we'll plug in that value and be able to solve for a particular solution because we'll know what c is. But for now, this is an indefinite integral, and we will always end up with the plus c. Now, we will also be finding what's called a definite integral in the second video, and in that case, we're going to have limits, x values, that will give us an interval on which we're finding the function by doing the antiderivative, and we will plug in those limits and actually get a numerical answer. But for now, all of our answers are an infinite family of answers. So you find the antiderivative, this is called your integrand. You find the antiderivative or the integral of it, and you put a plus c because there may have been a constant, okay? Long explanation for something simple. 1 is the derivative of x. If that was a 2, I would get a 2x. If that was a negative 18, I would get a negative 18x. Got it? Good. Okay. Second row. If y was x squared, then the derivative of y would be 2x to the 1, right? Because we multiply by the power and we subtracted 1 from the power. So if I integrated 2x to the first power, I would get x to the second power because 2x is the derivative of x squared plus the constant of integration. So for any power of x, when I take the derivative, I multiply by the power and subtract 1 from the power. So what did I do? I multiplied by the power, then I subtracted from the power. How do I do that backwards? Well, because we're undoing, right? I not only have to divide and add, I have to do them in the opposite order. So the way to do this is to add first, and then I'm going to divide by that. So the process of doing an antiderivative on a power rule derivative is down here. This is the power rule integral. If I have x to a power, dx, I'm going to add 1 to the power first, then I'm going to divide by the new power. Isn't that what we did here? We added 1 to this and got x squared, and then we divided by the new power 2, which canceled that out and gave me this. This guy right here, this constant, that's x to the 0. When I added 1 to the power, I got x to the 1, and that was divided by the 1. Do you see that? So it always works, and it works whether this power is a whole number, whether it's a negative number or fraction or decimal, as long as it's just a real number exponent. We're going to add 1 and divide by the new power. And don't forget the plus c. Okay, now the properties of derivatives say that I can take, if I've got a bunch of terms, I can take the derivative term by term. Well, it's the same thing with an integral. Also, if I have a coefficient, that guy's just going along for the ride. I'm integrating the x squared. Okay, so for this polynomial, I'm going to integrate this term by adding 1 to the power, dividing by the new power. That gives me x to the 4th over 4. When you get the hang of it, you do not have to write this line, okay? You can go straight to here and simplify as you go. All right, so I'm going to get x to the 4 over 4 for this. The minus 7 is just going along for the ride. I'm integrating this, so I'm going to get x to the 3 over 3, this guy right here. The plus 4 is going along for the ride. I'm going to get x to the 2 over 2, which is the 2 on the bottom will cancel with the 4 on the top and give me 2x squared. Minus 3 is the derivative of minus 3x. And then I have my constant of integration. And there is my final simplified answer. Okay, trig functions. If we have y is sine, the derivative is cosine. So it makes sense that if I integrate cosine of x with respect to x, I get the sine function back. These are just basic derivatives. We're not dealing yet with having some number multiplying the x that's inside the cosine function. We're not dealing with this being some other function, some u. That's going to come later. So for now, it's just plain sine, cosine, tangent like that. So if the derivative of sine is cosine, then the antiderivative of cosine gives me back the sine. But when I take the derivative of cosine, I get a negative sign, right? The sine and cosine are each other's derivatives, but when we take a derivative of something that starts with a c, we get a minus, right? Now, if I integrate plain old sine, My answer has to have that minus because the perfect derivative was negative sign. So I'm going to do this little simple trick, which you'll see more of when we get to integration by substitution. If I multiply by minus and I multiply by minus, I get a plus. So I haven't changed the value of this at all. But negative sign is the derivative. So when I take the antiderivative of negative sign, I get cosine. But I had to do this little adjustment. So what I'm telling you is the integral of the sine is negative cosine. So don't get confused with, whoops, I didn't mean to do that. You didn't see what I did. Don't get confused with, it's not letting me erase here. Don't get confused with the minuses and the pluses. Always think in terms of derivatives. What is the sine the derivative of? Well, it's the derivative of cosine, but it needs a minus. So your answer has that minus to adjust. All right? Derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. We don't know yet how to take the integral of plain old secant because plain old secant isn't the derivative of something simple yet. So we'll get that later. Right now we're integrating these perfect derivatives to get back the original trig function. The derivative of cotangent is minus cosecant squared. Again, that minus sign is going to come back. We're going to integrate cosecant squared, and we get cotangent, but it should have been a minus here. That gives us a minus on the outside in the answer. The integral of secant tangent, you ask yourself, what is secant tangent the derivative of? It's the derivative of the secant. So the antiderivative of this gives me back the secant. The antiderivative of cosecant cotangent, well, minus cosecant cotangent was the derivative of the cosecant. So we end up with minus cosecant when we antiderivative this thing. These are things that you're going to have to memorize, but you've already memorized the derivatives, right? I hope. So if you remember the derivatives, then you should be able to take the antiderivative very easily. You just always ask yourself, what is this the derivative of? And then you write down your answer. Okay, power rule derivatives are really, really simple. So a textbook has to make it difficult. Just saying. All right. So if you're given this, you don't have the tools to do a quotient rule. So what you have to do, this is just a single term in the denominator. So you're going to divide each piece of the top by this single. You can't just cancel. You have to factor out an x and cancel it then, or split this into two fractions and rewrite it before you take your integral. Once I've rewritten it, this is simple. This is x to the 2 over 2, and this is 4x. Boom. Plus a constant of integration. Here, it's the same as doing a polynomial. I'm going to integrate the sine and get negative cosine, and the 4 is just going along for the ride. Here I'm going to integrate cosine. Cosine is the derivative of the sine, and I get the minus 3 going along for the ride, plus a constant of integration. Again, you don't have the tools to do a chain rule integral yet. So we've got to FOIL this thing out. And this is not x squared minus 16. Guys, it's not. You can't distribute an exponent. You have to multiply this blob times itself, FOIL it out. Don't be lazy. Now I can just integrate term by term. I get x to the 3 over 3 minus 8 times x to the 2 over 2 plus 16 times x plus c. This is what it is. This simplifies to be minus 4x squared. You always reduce your fractions to lowest terms every single time, okay? Next problem. You will see mixtures of stuff. This guy is just x to the 3 over 3. This is a 5x plus 5x. This is a minus 8 times, what is the secant squared the derivative of? Tangent. And it's got the minus 8 going along for the ride, plus c. All right, radicals. Remember, radicals are just powers, exponents, right? So x, the top is the power, and the bottom is the root. So anytime you have a radical, the top is the power, the bottom is the root. You rewrite that, and then you integrate using a power rule. So I'm going to add 1 to this, and adding 1 means adding 2 halves, which gives me x to the 3 halves divided by 3 halves. Now when you divide by a fraction, you're going to flip this over and multiply. So the 2 is on the top and the 3 is on the bottom. The power, the top is the power, the bottom is the root. So I've got x to the 3rd power, 2nd root. And that's how you do the integral of a radical. This guy right here, I've got a plus 4. I ask myself, what is cosecant cotangent the derivative of? And it is the derivative of the cosecant, but it should have been negative. So that changes that sign and gives me the cosecant, and I have a plus c at the end. Okay, sometimes we have an initial condition or a boundary condition. I shouldn't have said initial there. Let me add and boundary. An initial condition is where you plug in a 0 for the x. Condition. Okay. Initial conditions and boundary conditions. So we're given this fact that if x is 1, y is going to be 7. And the derivative of the f of x is this. And we want to find the particular solution, the very exact f of x, because we're given this constraint here that we can use, this boundary condition, assuming that 1 is on the end of an interval here. Okay, so we are going to take the integral of this, or the antiderivative. I'm going to add 1 to the power, which makes that a 3, and divide away that 3. That gives me this, right? You, when you get good at this, you don't have to write this step. I'm telling you, you don't have to, okay? Because you know things are going to cancel. You're going to divide that 4 by the 2, which is going to make it a 2. You're going to divide that 3 by the new power, which makes it go away. And 5 is just the derivative of 5x. Then we have this constant of integration. So here's my antiderivative, or my integral, but I have to apply that condition. I'm going to plug a 1 in for each of these x's, which gives me 1 minus 2 plus 5, plus the constant of integration. But we're told in the boundary condition above that f of 1 equals 7. So all of this adds to a 4. I have 4 plus c, and that has to equal 7. Therefore, my c equals 3. And now I have a particular solution instead of a general infinite family of solutions. I found the exact value of my constant, and this is my answer. So I just integrate, don't forget your constant, then I plug in the value that's given, and I set that answer equal to the value that's given in the question and solve for C. Okay, here's some practical use here. A ball is thrown upward. It has an initial velocity, and if I'm throwing this ball or ejecting this ball out of something, I don't think I could throw a ball 30 feet per second. I mean 60 feet per second, but I was copying out of the book. So When it leaves my hand or it leaves the launcher or whatever, it's going 60 feet per second. Once it leaves my hand, the only force acting on that ball is gravity. So it has an initial velocity. If I'm throwing it upward, gravity's pulling it down, right? I'm throwing it up, but gravity is going to slow it down until it stops. The ball always comes to a complete stop at the top before it stops going up and it starts going down. Now, from what we learned on the last test, this is a parabola. If we're graphing this, that point right there, the vertex, that has a horizontal tangent, and the derivative of my function right there is 0, because the velocity, or it starts, it's increasing, it's going up, and then it stops before it starts to go down. So that point right there will be where the velocity of that ball is exactly 0. Okay, so it leaves my hand initially at 60 feet per second. At this point, it's at 0 feet per second. Then gravity is going to pull it down, just like gravity was working against it to slow it from 60 feet per second to 0 feet per second. All right, so we have this initial condition here of 60 feet per second. Then we also have an initial condition on the position of the ball. It started out at 100 feet above 0, or above ground level here. So if we started at 100, we're going to go up until gravity makes it stop, and then gravity's going to pull it down, and then it's going to hit the ground. And the height at the ground is 0 feet, whereas the initial height was at 100 feet. Now I'm going to ask you, given just gravity, which we're supposed to know, and these two initial conditions, how high will the ball go? What is the position of the ball here? And we can do that by figuring out how long it takes to stop. And when will the ball hit the ground? When is time? So the variable in all of this problem, we're given a rate right here. Do you see it? Feet per second. That's a derivative, and it's a time derivative. So we have 60 feet per second equals a time derivative, right? And it's the derivative of what? Velocity is feet per second, so it's derivative of, we're going to use s to represent position with respect to time, okay? Over here, s of t, it's a function of time, that's my position function. If I take the derivative of s, the rate of change of the position is the velocity, and we can also call that v of t. So v of t is the derivative of s of t. If I take another derivative, or the second derivative of the position, that's the derivative of the velocity. The rate of change of your velocity is your acceleration. We've looked at it so far as the curvature. But remember when we had a curve like this, it was increasing the whole time, right? But here, it's accelerating. Do you see the acceleration? This is concave up. The second derivative is positive. And then we have our inflection point. And now, while the first derivative is still positive, we're still increasing, the second derivative is now negative. Do you see how I'm increasing but I'm slowing down? If that continues, I'll eventually start to decrease, correct? So this shows me acceleration is positive, and here acceleration is negative. So all of this stuff is important to what we're doing now. All right, so we have The second derivative of position is the rate of change of the velocity, which is acceleration. So I know the acceleration of gravity. Because the question was in feet per second, it's minus 32 feet per second squared, okay? So this is a rate of change, and it's feet per second squared. That makes it the second derivative with respect to time. So I'm going to write that down as well. If I have, watch my notation, the second derivative of the position with respect to time twice is gravity, and that's feet per second squared. You see how I have the derivative of time twice on the bottom? That's per second squared. So these are things that we need to know, and we also need to know our initial condition. At time 0, the position was 100 feet, okay? And we're going to call this S naught or S0, and that equals 100. We were also given an initial velocity. I know I've written this somewhere else, but the velocity at the beginning was 60 feet per second, and we're going to call that V naught. Okay, so there's my notes. Let's work this problem out. We know that A of t is minus 32. If I integrate this, the acceleration is the derivative of the velocity. So velocity will be the antiderivative or integral of the acceleration with respect to time. So I integrate this with respect to t, and I get minus 32t, right? The derivative of the t integrated gives me a t, plus some constant. But if I plug 0 into this function, my initial velocity, v naught, this guy goes away, I'm left with my constant, and that is 60. So you can remember that velocity is minus 32t plus v naught. It's always that. I'm going to make a note at the bottom here. So velocity is always minus 32t plus v naught. All right? Okay, so where are we now? So we've got this as our velocity for this problem, but velocity is the derivative of position. So if I integrate this, I'll get the position function. So the integral of this, I'm going to add 1 to the power, makes it t squared, and divide by the power, right? And then I integrate this. 60 is just the derivative of 60t, because it's with respect to t, don't put an x, plus some constant. Well, we already know what's going to happen. First off, this is minus 16t squared plus 60t plus a constant, but the initial position, S naught, was 100 feet. So my C, this is a 0, this is a 0. When I plug in the 0, my constant was 100. And I get this formula or function which represents the position of the ball at any time t. So we always know that the position function, it will always be minus 16t squared, and the coefficient of the t term is always going to be the initial velocity integrated, so it's time t, plus the initial position. So you always have this, and you always have this. If the only thing acting on the object is gravity, you always have those things. All right, now I asked 2 questions. I asked, how high will the ball go? Well, if it starts here and it's thrown up, what do I know about this position right here? Well, it'll be the vertex of this parabola, but it will also be where my velocity was 0. I left this point with an initial velocity. Gravity is negative, it's pulling down, correct? So if I stopped right here, that meant my velocity would be 0. There's no movement. So the vertex of the parabola is where the derivative equals 0, right? Or we can see it in terms of the ball stops. So the way to solve that is to set velocity equal to 0 and find t. Once I find the t, then I have to plug that in to my position function to see how high it gets, okay? So you find the time first, then you find the height. Next question, when will the ball hit the ground? Well, what's the position when it hits the ground? Position equals 0. So I'll have to set this function equal to 0 and find the time that it takes for it to smash on the ground. We're going to do all of this in the next page. Okay, so we have our position function and our velocity function. When we find how high it goes, we're going to take the velocity because the ball stops at the top, right? Set that equal to 0 and find the time. 4 goes into both of those things. Seconds is the unit of time that we're using. So now how high? I take that time and I plug it into my function. Yes, I know. Pain in the neck. But the coefficients will help. Don't we love fractions? All right. When I'm squaring this thing, I'm going to get 15 squared on the top and 8 squared on the bottom. Well, 8 squared is 64. 16 goes into 64. How many times? 4 times? I get 15 squared. You guys don't have to do it this way, but I choose to. 15 squared over 4, negative, plus, next term, 8 on the bottom. Well, 4 goes into, no, I want a 4 on the bottom. I'm going to take a 2 from this and divide this, and I'm going to get 30 times 15, which is 2 15 squareds. These are just numbers, and I know you guys are going to use a calculator. Common denominator is 4. I like to do things by grouping. Sorry. All right, negative 15 squared plus 2 15 squareds is going to leave me with 15 squared over 4. See how that works? I have 15 squared over 4 plus 400 over 4. And now all I have to do is square a 15. And I'm too lazy to reach for the calculator, so give me a second here. 15 times 15, I have 10 of them. Then I've got 5 times the 10 and 5 times the 5, and I get 225. Okay, so 225 plus 400 gives me 625 over 4. That's feet, and it doesn't reduce. And this is an exact answer. You can divide and do it as a decimal if you'd like. I'm going to leave it like it is. All right, next question. We have the maximum height that the ball goes. The next question is when will it hit the ground? Well, we have the position, and we want that to equal 0. So minus 16t squared, yeah, you're going to have to use some stuff here. plus 60t plus 100. And I've noticed from tests, you guys need to work on your algebra, so we might as well. I'm going to factor out a -4, which doesn't do anything for an answer because 0 divided by -4 is still 0. So I got 4t squared minus 15, love the 15, t plus 25. And I'm not going to try to factor it because I'm lazy. T equals -b plus or minus the square root 15 squared. I've already done that. I know what that is. Minus 4. A is 4. C is 25. All over 2a. So T equals 15 plus or minus, wait just a second, that's going to give me two answers. How are we going to know which one's correct? Well, it's going to be the one that makes sense, right? Time is starting at 0 when the ball is at 100 feet. It's going to move forward, so my answer has to be positive. Time is always positive, right? And the answer will just make sense once we get there. So inside the radical here, 15 squared is 225. I have minus 25 times 4 is 100. Something is wrong. Oh, do you see the mistake I made? How do I know something's wrong? Because this guy was going to be negative, okay? And time can't be imaginary. Ooh, that's a cool concept. Time can't be imaginary, so, or complex. Boy, my time's gotten very complex. This can't be minus. So I have to go back and see where I made a mistake. I pulled out a -4. That's a minus. That should be a minus. So learn from my mistakes, guys. This is a negative. That makes this 25 in here a negative. I'm going to need to rewrite that. -25, which means now under the radical, I'm adding. 4 times 25 is 100 times 4. Booyah. I'm going to get that same number I got before. Funny how that works out, huh? Over 8. 15 plus or minus the square root of 625. All over 8. And guess what? This is plain old 25. So I've got, to make this smaller, I have t equals 15 plus 25 over 8, or 15 minus 25. Do you see what I mean by one of them will make sense? I can't have negative time, although it feels like it all the time. 15 plus 25 is 40 over 8. Wow, pretty problem. They don't always work out this nicely, guys, just showing you. This is how long it takes to hit the ground, and this is its maximum height. Cool problem, huh? Fun stuff. Get on it.